that we have used for our study. So these three are the initial conditions for the different configurations. The first one is the configuration that is used by Vasilev and Kraiko. This is of a moderately strong shock. Even though we say weak shock reflection, this is kind of strong shock, but it is still in the weak shock reflection domain. And this is the configuration for which Vasilev and Kraiko found the existence of a single supersonic patch. And later, for the same configuration, Testel et al. Found the existence of multiple supersonic patches for the same configuration. The second one is the configuration investigated by Testel and Hunter using the unsteady transonic small disturbance theory. And this is the first configuration that for which the existence of multiple supersonic patches was found and investigated. And this is also close to the configuration that is used in experiment by Skews et al. And this is also a very weak shock. This is that was investigated by Testel and Hunter. So this is the pressure solution obtained for the first configuration, which is the a Mach 1.47 shock reflecting over a wedge of edge angle 12.5 degrees with gamma is equal to 5/3. And this solution is obtained at T is equal to 0.32 using P4 based DGM with a grid size of H is equal to 1/800. And we propose to, we have used an overset grid here at this location, and we have resolved it further. And we have looked at the sonic line to see whether supersonic patches have increased or what happens to the solution there at the triple point. And in the same overset grid, refined overset grid, we have used viscous fluxes to see further what happens. So now first I will show the zoomed in location. I mean, I'll zoom in the solution at this location by about 3 orders of magnitude and show the solution there. Here, I show the pressure solution for the grid size H is equal to 1/800 for the full solution for which I have shown before. And I show the sonic line where the self-similar Mach number is equal to 1. Here we can see that the sonic line follows the triple point quite closely. I mean, this shock marks them quite closely, and we don't see any existence of supersonic patches for this configuration. But when we resolve this further using an overset grid, when we use an overset grid of H is equal to 1/1600 at the same location, we see the existence of multiple supersonic patches. So this is again the sonic line, and we can see that the small supersonic patches have been forming. And I reiterate that this is the solution for which Vasilev and Kraiko found the existence of a single supersonic patch, and Testel et al. Found the existence of multiple supersonic patches. And we have found multiple supersonic patches for this grid resolution using overset grids. And when one more thing is, which wasn't done anywhere else, one more thing is we have added numerical fluxes on this overset grid, and the number of supersonic patches have increased. And even the size of the supersonic patches have increased. This is an interesting observation we have found. And the same thing happens for the other configurations. For the second configuration, for which the weak 1.075 shock reflecting over a wedge of angle 15 degrees and gamma is equal to 7/5. Near triple point, we show the sonic line at T is equal to 0.3 using a grid size of H is equal to 1/800. And here it is interesting that we can see some small supersonic patch forming, a single supersonic patch forming. No, actually there is one more supersonic patch forming, 2 small supersonic patches forming here. And when we refine the grid further, the number of supersonic patches have increased. And when we add viscous flux, so the same thing happens for the third configuration, for which a very weak shock of Mach number 1.04, reflecting over a 11.46 degrees wedge. And the solution is obtained at t is equal to 0.2. And from the sonic line, here we can see that two small supersonic patches are starting to form. And when we resolve the grid further, we see the existence of multiple supersonic patches. And when we add viscous fluxes again, we have more supersonic patches. So this is quite interesting that the number of supersonic increase in number of supersonic patches with the viscous fluxes. And we also mentioned that Skews et al. Found the size of the supersonic patches that they have observed experimentally to be larger than the size of the supersonic patches that were found numerically. So this is still, we have to really see what is happening, what is the real configuration that actually resolves the paradox. To further study this, we are planning to obtain a fully viscous solution and see the transient formation of the shock and the formation of the supersonic patches to investigate this further. So to conclude, we have investigated the weak shock reflection problem in inviscid and viscous flows in the von Neumann paradox regime. And for the three configurations we have considered, we have observed that refining the grid near the triple point increases the number of supersonic patches, and adding the viscous fluxes further increases the number of supersonic patches. And these numerical solutions again lend credence to the observation reported by Tesdell et al. In 2015 that the single supersonic patch structure is not a distinct reflection geometry, but it is only an under-resolved multiple supersonic patch structure, which is also known as Gooderle-Mach reflection. And to further study this, we are planning to obtain a fully viscous transient solution to really study how this supersonic patches are forming, to understand the physics behind the formation. Thank you.
I'd like to thank Mr. Kochi for a very nice presentations. Time for a couple of quick questions, perhaps.
Hi, I just have one question mainly, which is like when you resolve the grid, you said there are more of these formed. And when you change the resolution of the grid, was the size of the very first patch increasing, or was it physically same size?
It is increasing, kind of.
Then it could be something artificial, right? So you're zooming in more, so I cannot tell whether physical size, is it the same or different?
In fact, we don't have any supersonic patch here.
Okay.
Yeah, we can't see any supersonic patch here. And when we resolve it
all
further,
of these are same resolution you're showing?
Yeah, same resolution.
As in, sorry, not same, same width.
Same width, same width, same physical width.
Okay. So this could be some artifact of your gridding or maybe some numerical calculations?
No, in fact, when we refine the grid further, the artificial viscosity, the effect of the artificial viscosity decreases. So it's actually more close to what fully inviscid solution.
Okay, but in real life, they are saying viscous solutions, right?
Yeah, that's what is interesting. When we add viscous fluxes, this further increases. The size of the supersonic patch remains the same, but the number of patches increases. So
this is going against.
Yeah, that's what is interesting. That's why we want to study the fully viscous solution to see why it's against the whatever explanation. I mean, that's what the explanation Tessel et al. Gave.
What is the physical size that is observed by Tessel or by SKUs over
The,
whichever group?
the physical size observed by SKUs is actually larger than
How big
at
is it?
the
Is it like
kind
3
of-
times, 5 times,
no, about 2 times.
2 times?
About
this
2
size?
times.
And that is viscous. It's
That
real
is
life
viscous. That is obviously viscous. So we don't know whether this when we go further, refine it further and further, whether they will coalesce and more become more close to whatever the solution. I mean,
Did you see any coalescence in your refining till now?
no, I don't see any covalence.
What is that
Yeah.
first patch looking like some double petal kind of?
Yeah,
The very first patch from the top looks like it's a double petal, no? Is it
yeah,
some form of coinciding that's
yeah,
happening?
yeah.
So there is a possibility that there is some coinciding happening and they'll club together to form a
Club
bigger
together.
patch.
Yeah. It's a possibility. It's a
But the
possibility.
only thing that's going against all your hypothesis is that you are making it more and more inviscid.
Yes, and we add viscous fluxes. It is
And it is trying to match a viscous
Match-
flow.
yes,
I don't understand
yeah.
that part. You're also not clear.
yeah. We are not clear on that. That's why we want to study this further.
Any other questions? A quick one maybe. Yeah.
Very good work, Shiv Prasad. We have been looking for something like this for a long time. But in Skew's paper, I remember that there is an expansion fan forming from the slip line, right? Here, there is no slip line seen at all.